questions 21 through 25 on the 2015 grade 10 Cayley math contest. The average of a list of 3 consecutive odd integers is 7. When a fourth positive integer m, different from the first 3, is included in the list, the average of the list is an integer. What is the sum of the 3 smallest possible values of m? Well, we have 3 consecutive odd integers. So an odd integer will be of the form 2n plus 1. So if I have 3 consecutive, 2n plus 3 and 2n plus 5. Now we are taking the average of those, so add them up and divide by 3. And they're saying that's 7. Okay, so this would be 6n plus 9 is equal to 21. So therefore 6n is equal to 12. Therefore n is 2. If n is 2, those integers were 5, 7, and 9. And some of you probably could have figured that out without doing this math, but it's important to do the math to illustrate how to be sure what these numbers are. Okay, so now what they're doing is they're taking those numbers 5, 7, and 9, and they're adding some new number m. And they're saying that when you take the average of these 4 numbers, you get an integer. Okay. Well, 5 plus 7 plus 9 is 21. So 21 plus m divided by 4 has to be an integer. All right, so very quickly you realize that the numerator has to be divisible by 4 in order for this to become an integer. So let's see. M, of course, has got to be a positive integer. They even tell you that. Positive integer m. So what can m be that makes it divisible by 4? Well, the numerator, first of all, can be 24. If the numerator is 24, that means m is 3. The next numerator that would make it divisible by 4 is 28. If the numerator is 28, then m would be 7. If the numerator is 32, m would be 11. And there you go. I just got 3 smallest possible values of m. Or did I? This question's tricky, because you might be tempted to end the question right there. You say, well, I got 3. Let's add them up. I've got to find the sum. The sum of these 3 is 21. Circle 21 and off you go. Well, that's wrong. So why is it wrong? I did everything correct. So far, yes, but there's one line in this question right here. M is different from the first 3. So M, this letter, is different from this, this, and this. And if you notice, 7 appears there, so I cannot include 7. It has to be different from the first 3 numbers. And I think that's the part of the question that is tricky. And what they do on these contests is they anticipate the wrong answer, and that's why they put the 21. If they didn't put the 21 in there, and you got 21, and 21 is not one of the answer choices, it would force you to go back to the question and figure out, why did 21 not appear? But when 21 does appear, you select it and unfortunately get the wrong answer. So it emphasizes how important it is to read the question carefully. Okay, let's keep going. The next one would be 36. If the numerator is 36, then that means m is 15. Let's check. 3, 11, and 15, are they different than those 3? Indeed they are. So those 3 are the ones that I have to add up. 3 plus 11 plus 15. And those 3 add up to 29. So number 21, the correct answer is D. Six players compete in a chess tournament. Each player plays exactly 2 games against every other player. In each game, the winning player earns 1 point and the losing player earns 0 points. If the game ends in a draw, each player earns half a point. What is the minimum possible number of points that a player needs to earn in order to guarantee that he has more points than every other player? Well, let's see here. Each player plays exactly 2 games against every other player. So there's 6 players, so each player, let's say A, B, C, D, E, and F represent the players. Each player is going to play the other 5 players twice, so each player plays 10 games. 10 games per player. So what we have to do is create some scenarios, see if, looking at the answer choices, which one of these work and which one of these don't. And I guess take it from there. So let's do that. So let's start off with A, B, C, D, E, and F, and let's try to make somebody have 10 points, and let's see if that guarantees that he will have more points than everybody else. If he has 10 points, that means he got those with 10 wins. 10 wins, 0 draws, 0 losses, right? So the number of points for player A is 10. If he had 10 wins, then that means there was 10 losses, right? Every game that he won, somebody lost. So we have to distribute them evenly. So 2L, 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 like that. Because he won every game he played. So every single game the other players played against him, they lost. So that's why it's 2L like that. Okay, now let's talk about B. If B lost 2, let's say he won the other 8. So we have to now distribute those 8 losses that the other teams had among the other 4 players. So we can distribute them evenly, 2L, 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 like that. Same sort of scenario. If C lost 4 games, then let's say he won 6 games. We have to distribute those 6 losses to the other teams. So 2L, 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 and 2L. D lost 6, so 1, 4. Distribute those 4 losses evenly among the other 2. E finally lost 8, 1, 2. And we distribute those to F, which would be 0 wins. Now let's tally up the points. The points looks like 0, 2, 4, 6, 8, and 10. So without a doubt, if a person scores 10 points, he's guaranteed to have more points than any other player. So this is fine. But we want to see if any of these can also guarantee. All right, no problem. Let's keep that in the screen and let's do the exact same scenario. This time for 9.5. And let's see what we get. Since the next answer choice is 9.5, we want to try to see if a scenario of 9.5 can guarantee a situation where one player has more than every other player in terms of points. Well, a 9.5 will be obtained if you have 9 wins and 1 draw, because you will get 9 points for the wins and a half a point for the draw. So that would give you 9.5 points. Now we have to now start thinking about all the other guys. Okay, well, if we distribute the draw to the very next player, right, because if he drew one game, then he had to tie with another. So that draw has to match with some other player. Let's just say it's with B. And then now let's proceed pretty much in a simple way. If this guy has a draw, he can't have 9W, 0 losses. He can, but if that's the case, it'll be 9.5. And that's the same. We want a scenario where A has more points than every other player. Okay, so that's no good. We don't want to give 9 wins. So let's give 8 wins. And also what's very important to mention is that even if you tried to give 9 wins there, it wouldn't work, because when you distribute the 9 matching losses, you have to distribute them evenly. And if you did 2L, 2L like that, this is now 12 games. And remember, a player only plays 10 games. If you distribute them evenly, like 2L, 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 and 1L, you're still 11 games. So that's another very important thing to illustrate, that even if you wanted to, you couldn't put 9W. So you have to put 8W in order to make things match. 8W works with one draw, but remember that only accounts for 9 games. So that means there had to have been one loss here. So the other 8 losses for matching player A's 9 wins have to go here. 2 losses, 2 losses, 2 losses, 2 losses. Okay? Now we have to account for those 8 wins and the matching losses. So we can distribute them evenly. 2 losses, 2 losses, 2 losses, like that. C, let's just keep it simple and say he lost 4, so he won 6. Distribute those 6 losses. D lost 6, so won 4. Distribute those 4 matching losses. E lost 8, that means he won 2. Distribute those 2 losses, and then that means F has 0 wins. So the points will be as follows. We have 9.5 as previously calculated. Here will be 8.5, and then the rest will be 6, 4, 2, and 0. So this is a scenario that clearly guarantees that 9.5 for A is greater than every other. But it actually doesn't guarantee it 100% because I have to create other scenarios. Now, the first scenario is right here. Another scenario I'll do, and then later I encourage you to see if there's any other scenario that you can create that negates this, but you won't be able to, because you won't be able to get any scenario that matches up like I did with the 9 wins here. You remember? It created a scenario where you couldn't get 10 games. It would be either 11 games or 12 games, and it wouldn't work. Another way is if you have 9 wins, 1 draw, 0 losses, but instead of putting the draw here, I'll put the draw way out with another player. So let's say I'll put the draw with F, 1 draw here. And then I will give this guy 8 wins, but I'll give him 0 draws. And then I have to now distribute those 2 losses. 9 losses, I should say. So here we go. So we'll do 2 losses, 2 losses, 2 losses, 2 losses, 1 loss. But that's pretty much the same thing as this. I just interchanged B and F. So let's make it a little bit different than that. Let's put 1 loss here and 2 losses there. That makes a little bit different. Okay, so we accounted for those 9. How about these 8? We have to write 8 losses now. So 2L, 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 2L. That means if this is 4, we can make that 6W, account for 2 losses each to make that 6 losses. This D now has 6 losses, so 4 wins. Account for those 4 losses. This is now 7 losses, so 3 wins. We have to account for 3 losses. So the only guy I can put is there, but the problem here is now this overcounts. We have 12 games and F is only allowed 10. So as you can see, it doesn't match. So the only way to make it match is to have a scenario like this. So in a very thorough way, I hope I have illustrated that this is sort of the only way of doing it, and therefore it guarantees that with a score of 9.5, a player will have more than every other player. Okay, so this is also good. So now we have to see about 9. Now let's see with 9, A, B, C, D, E, and F. Okay, the only way to get 9 points, or one way to get 9 points, is to have 8 wins and 2 draws. And when you do that, you now have to, in the same way, account for the 2 draws with some other player. So if player A played 2 games and both games were draws, there was another team that also drawed with him, or another player, I should say. So that means that we'll make B the player that he tied with both times. So in a very similar way, this has got to be equal to 8. But before we put that in, let's account for the losses. Now, he already played B twice, so he didn't lose to B. He tied with B twice. So no losses can go here, accounting for these. So the other losses have to be distributed among the other players. So that means that since there's 0 losses here, this was 8W. Now these 8 wins, we have to account for those via losses. So we put 2L, 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 2L like that. Here's 4 losses, 6 wins that means, so account for those with the other players. Here 6 losses, that means 4 wins, account for those. Here E, 8 losses, 2 wins, account for those, and this is 0 wins. So let's see what the totals are now. This is 9, this is 9, this is 6, 4, 2, and 0. Well, now we have to discuss this. What we found is a scenario that works, meaning everybody plays 10 games. There's no overcount, there's no 11 games, 12 games, that kind of problem. But notice, even though A has 9, he doesn't have more than every other player. He actually has the same as B. So this is where we have to start discussing this question. Basically what that means is that since we found a scenario where having 9 points does not guarantee that a player has more points than all the others, 9 points does not guarantee that a player will have more points than any other player. So that scenario basically shows that having 9 points does not guarantee that a player has more points than all the other players. This scenario is a perfectly valid scenario because all the players have played 10 games, and when I calculated the points, as you can see, 9 points is obtained by player A, but it's also obtained by player B. So we are now concluding this question. As I've shown above, if a player has 10 points, which was shown here, or has 9.5 points, it is guaranteed that that player will have more points than all the others. But if he has 9 points, like here, it is not guaranteed. So to repeat, as shown above, if a player has 9.5 or 10 points, it is guaranteed that he or she will have more points than all the other players. But if a player has 9 points, it is not guaranteed. So that means the minimum number of points that are guarantees a player to have more points than all the others is 9.5, which would be right here. And that is the final part of the question. Therefore, the minimum number of points that guarantees having more points than all the other players is 9.5. And therefore, the answer to number 22 is D. Nyla has her living room lights on a timer. Each evening, the timer switches the lights on randomly at exactly 7, 7:30, 8, 8:30, or 9 p.m. Later in the evening, the timer switches the lights off at any random time between 11 p.m. and 1 a.m. For example, the lights could be switched on at exactly 7:30 p.m. and off at any of the infinite number of possible times between 11 p.m. and 1 a.m. On a given night, Nyla's lights are on for T hours. What is the probability that T is between 4 and 5? Well, let's create some scenarios. And of course, our starting point is 7, 7:30, 8, 8:30, and 9. And each of these are randomly selected by the timer, so they obviously are occurring with equal probability, which is a probability of 1 over 5, since there's 5 times, and each of those is selected at random. So that's the first part. Now we have to figure out what is the range for each of these. Well, if it starts at 7, it goes anywhere between 11 p.m. and 1 a.m. So 11 p.m. to 1 a.m. is sort of the boundaries. And what that would create is times of 7 to 11 is 4 hours, but 7 to 1 a.m. is 6 hours. So time in this scenario can be anywhere from 4 to 6 hours. Now we want the time to be between 4 and 5 hours. Okay? Well, 4 and 5 hours, that is a 1 hour time period, and 4 to 6 hours is a 2 hour time period. So one of those 2 hours is basically a probability of a half. So I hope you understood that. If you didn't, not a problem. I can draw a little number line here and illustrate that a little bit more carefully. So let's say we've got the span here is between 4 and 6 hours, right? From there to there. And we want the span to be between 4 and 5, which is from here to here. So we basically want from that whole possible span just this much, which is obviously half. So that's why I put half. Half of that interval. Now we have to calculate the probability. How do we do that? Well, we take this number, we multiply by that number. The probability of starting at 7 was a half. The probability of then starting at 7 and having an interval between 4 and 5 is a half. Sorry, it was a fifth and a half. So when you multiply them, you get a fifth times a half, and that is 1 over 10. So I hope you get the hang of that. Now let's do the exact same thing for all the other guys. Again, 11 p.m. to 1 a.m. This span now would give you from 7:30 to 11 would be 3.5 hours. From 7:30 to 1 a.m. that would be 5.5 hours. So this time our interval, if you started at 7:30, is from 3.5 to 5.5. So from there to there, that's the full interval. But we don't want the full interval. We only want, as always, the time to be between 4 and 5. So look at our interval. We want basically this part of that interval. Instead of from 3.5 to 5.5, we only want it from 4 to 5, which is half of that interval. So the probability of having the interval between 4 and 5 within this range is a half. So now we have to calculate the full probability, which would be 1 over 5, the probability of starting at 7:30, and 1 over 2, the probability of time being between 4 and 5 within that full range. So again, 1 over 5 times 1 over 2, which is 1 over 10. So by now you're an expert, so I can go through the rest of these pretty quickly. 11 p.m., 1 a.m. time, this time will be between 3 and 5. And then 3 and 5, of course, is this range. We want between 4 and 5, which would be that range. Well, that's a half. And there we go. Therefore, the probability would be 1/5 times a half once more, 1 over 10. 8:30, again, interval is the same in terms of its endpoints, but this t is not the same. That is going to be 2.5 and 4.5. And that would be 2.5 to 4.5. So from there to there, we want it to be between 4 and 5. Well, the only time it's going to be between 4 and 5 is that, between 4 and 4.5, and that represents 1/4 of that interval. So this is going to be 1/4 this time. Now the probability is 1/5 times 1/4, which is 1/20. And then now, finally, when it starts at 9, our interval this time is 2 and 4. So our range is between 2 and 4. Now, when is it between 4 and 5? Well, 4 and 5 is here. So the answer is never in this scenario. So 0 is the probability of it being between 4 and 5 if the range is between 2 and 4. Okay, so the probability would be 1/5 again, this guy, but multiplying by 0 this time, which is, of course, 0. Now we have to calculate the full probability, and the full probability is obtained by adding up these numbers, all of these numbers. And when you do 1/10, 1/10, 1/10, 1/20, and 0, you get 7/20. And 7/20 is E for number 23. In the diagram, a rectangular ceiling PQRS measures 6 by 4 and is to be completely covered using 12 rectangular tiles, each measuring 1 by 2. If there is a beam TU that is positioned so that PT is equal to SU equal to 2, and that cannot be crossed by any line, then the number of possible arrangement of tiles is. So what they are saying is that there is this beam that I will draw here, TU, like that. And we can't cross it. So we can't draw any tile that would lie across it like that. We've got to basically treat this as two compartments. One compartment here and one compartment here. And figure out how many different arrangements we have for each compartment. Okay, so what I will do first is concentrate on PTSU, which is the smaller one. So this one right here. And PTSU. How many different ways can I make PTSU using these tiles? Well, I have to think about this for a second. I probably first have to realize that I can only put 4 of these tiles, and this kind of illustrates it. 1, 2, 3, 4, right? That diagram. So if I can only put 4, how can I put 4? Well, let's just draw the scenarios, and once I draw the scenarios, it will make sense. If I break it up into 2 equal compartments like that, try to make them equal the best I can, then each of those compartments has 2 ways that it can behave. It can either have the tiles like that, or the tiles can be like this, right? So each of those will have 2, so 2 times 2 is 4. And since there's only 4, it won't take that long to draw them out. So 1, 2, 3, and 4. And let's just draw them out. So let's draw first the compartments, and then let's see. So the first one is like this. Second one like that. The third one like this. And the fourth one like that. You get the point. Not works of art, but these are the 4. Now you say, okay, well, is that it for just PTSU right now? I'm only concentrating on that. And the answer is no, there's one more. And that is probably a little tricky, not extremely tricky, but there's one more. And that is when you have the compartments like this, where you have them like this, but then this guy in the middle has 2 possible ways. You can either have it like that, with one down the middle like this, or you can have the other scenario, which is the same kind of thing, but as you can probably figure out, once you make that, the other ones would be like this. Okay, so how many did I draw? I drew a total of 6. But we have to be careful in this question because you're going to get a lot of overcounts. That's the key. In these 6, are any of them counted twice? And the answer is yes. Look at this one and this one. Those are the same. So this is an overcount. Overcount. So in terms of unique, I had 1, 2, 3, 4, 5. Okay. So for PTSU, I got 5 unique different arrangements. Now I have to concentrate on this guy. How many? And whatever it is, whatever that number is, in the end I have to multiply that by 5. And that's why all the answer choices are multiples of 5, as you can see. Okay, so now we are going to move on to TQUR. TQUR is a 4x4 square. And what initially I've done is I've broken up into 4 compartments like that. And each of these compartments has 2 possible scenarios that it could look like. One scenario, of course, is like that. The other scenario is like that. And each of those is the same. It could be like that in that compartment or like this. And the other one, the 2 tiles can look either like that or like this. And of course the same thing for the last one, like this or like this. So each of them has 2 possible ways, so 2 times 2 times 2 times 2, a total of 16. Okay, but we're far from being done. We got to keep going here. We got to figure out other scenarios. Okay, no problem. Let's see. How about if I have something like this? If I have tiles pretty much on the sides like this, but then my compartment in the middle is like this. Do you see how I switch things around now? Okay, well, these are fixed, so there's only one way of putting those. But these guys, these bigger squares, I've got 2 ways, either like that or like this, like that or like this. So each of those has 2 possibilities. So 2 times 2 is 4. But, as always, we have to look at overcounts. So let's quickly draw in the overcounts. We don't have to be, an artist here. We are just trying to show, can any of these overcount the ones that we've already created over here? Okay, well, let's see. First, let's draw them all. There's only 4, so I can draw them pretty quickly. Let's see, this guy. The first one would be something like if all of them sort of were horizontal. The next one is going to be if we have this guy horizontal, but this guy vertical. And then in another one, we can have this guy vertical and this one horizontal. And finally, the last scenario is one where we have both of them vertical, like this. Okay, now that we've got them all drawn, can any of these 4 have occurred already in these 16? And if you look carefully, the answer is yes, this one. This one is an overcount, because this one could have been created in this scenario also, if all of them were like this. So, okay, not a problem. That means we got 3 unique. 1, 2, 3. So we got 3 of these unique ones. So the unique ones, let's just circle them in red. I think that'll be easier for us. Okay, keep going here. We are still got a little bit more work to do. It's a time-consuming question, in all honesty. Let's see if I can get any more scenarios. And the answer is yes. All you got to do is just take this one and flip them. So basically take what I just did and flip it. And what I really mean by flip is turn it 90 degrees. So you basically are just doing this kind of thing, like that. And when you do, you will quickly see that it's the same kind of story. I don't need to walk you through it. And it will create 4 very similar arrangements like this. And let's draw those in really quickly. So we got this one down the middle, this one down the middle, that down the middle, that down the middle, and then we've got to basically make the different ones. This one, that down, up, down to the side, up, down, up, down. All right. I think that covers it all. Yeah. Okay, and as before, we've got to look at any of these overcount, and the answer is yes, this one is an overcount. So I'll just write that here, overcount. But we got 3 unique ones, 1, 2, 3. So I got 3 more. Okay, so far I got these 3. So 16, 3, and 3. Now, keeping in the tradition of these guys, can I make any more that look similar to these? And the answer is yes. If you take that square and draw the box in the middle, so like this, that would be one that would work. And then if you do a 90 degrees, it would basically create another scenario where you've just rotated, and that sort of helps us out and makes things a little bit easier for us. So like this. Now for each of these, you got 2 scenarios, right? Either the middle box can look like that, or it can look like that. Same thing here, either like that or like that. Well, if you make it look like this, it will be exactly like this guy. So that will be an overcount. So we have no choice but to make it look like this. And that's the only unique one we can get. So we have one more unique one there. So we'll circle that. And by the same principle over here, if I drew the line like this for the middle guy, it would make it look exactly like this. If it was drawn perfectly, but you understand. So the only choice we have is to make it look like that. And that's the only way we can get another unique one. So there we go. So far we have 16, then 3, 3, and 1, 1. Okay, but we still have a few more to go. We have 4 more scenarios to look at, but the good news is that they're very similar. They're scenarios in which we have now 3 2x2s, like that, as you can see. And then one of these will just be like individuals. So we have to rearrange these to put 3 2x2s. So that's one arrangement. Here's another one. Right? And then just do the flips. The 90-degree flips helps us out a lot in this question. It allows us to get other ones very quickly without having to put too much thought into it. And then another 90-degree flip would give you the last one, like this. All right. So now, for each of these, we got to figure out the different scenarios. Well, just based, without even drawing in the lines, this is 1, 1, 2 possible ways, 2 possible, 2 possible, and so on, right? And by now, you guys know why there's 2 for each of these, the different orientations. So 2, 2, and 2, well, looks like 8. It looks like this should be 2, 2, and 1. Again, 8, 8, and 8. Well, the good news is that you don't have to worry about 8, because watch what happens if I were to make a line that went across like this. This would be pretty much the same as one of these 16. We can make something that look exactly like that, exactly like this, if we just did this, right? So this is not unique. So that means for this particular shape, the only way to make it unique is to have a line straight down like that. So when you make a line straight down like that, it gives just 1 and 1. Those will be fixed, and therefore this immediately knocks down to 4, making our life a little bit easier. Okay, but are those 4 going to be unique? Meaning, are they going to be new or are they going to be overcounts? Okay, no problem. Let's draw them pretty quickly and see if they're going to be new or overcounts. Well, looks like the left side is fixed, so that's going to be the same. It's going to be like this. So now we just have to worry about the right side. Okay, let's figure out what possible scenarios. I can have that one. I can have this one where they alternate. I can have this one as vertical and this one as horizontal. And finally, I can have both as vertical. Okay, are all of these unique? Yes or no? And when you compare these 4 with the ones we've created above, you'll find that one is an overcount. And the one that is an overcount is this one right here. That's the same as this one, as you can see. They're not perfectly drawn, but you know what I mean. So since that is an overcount, we'll write that in there. Overcount. But these are unique, these 3. So we got 3 unique ones. And for the sake of time, the other 3 have the exact same story. Meaning, just like how I did with this guy here, you will immediately realize that for this box, if you drew it like this, it would basically be overcounted in one of these first 16. You would not create any unique ones. So the only scenario possible is for it to look like this. And that immediately knocks this down to 4. Right? Because then this would no longer be a 2, it would just be 1 and 1. Because those would then be fixed. And then when you create the 4 that is listed here, you would get those 4. And of course, as always, we have to go back and see, do any of these overcount any of the ones that were previously made? And when you compare, you'll see that one of them will. And in this particular case, this one overcounts with this one. So we will be able to eliminate 1. And that will knock down that 4 to 3. And then you will get 3 unique. So I think I've exhausted it. You don't need me to go through the next ones. This will also be 3. And this will also be 3. And you can do that in your spare time. So now let's count all the unique ones. 3, 3, 3, and 3. That's 12. Then we had this 1 and 1. That brings me up to 14. 3 and 3, another 6 is 20. And the 16 makes 36. So all that hard work to figure out that this is 36. And then, of course, you have to multiply them. 5 times 36 is 180. So number 24, a very time-consuming question. The answer is A. Rectangular prism PQRS WTUV has a square base PQRS. Point X is on the face TUVW so that PX is equal to 12, QX is 10, RX is 8. The maximum possible area of rectangle PQ UT is closest to. Let's first label this diagram. Let's say that point X is right here represented by that red dot So that is x. So we will join P to x, Q to x, and R to x. And then what I will do is I will drop a perpendicular directly down from x to the base, right here to that base. And I will then connect P to that base, and it will be exactly the same spot on the bottom base as the top base. So once I connect it to P, Q, and R, it will look like that. Now, this diagram is going to get pretty messy, so I will avoid anything other than the distances, which are 12, 10 for QX, which I can squeeze in right there, and 8. Now, at this point, what I'll do is, instead of working with that diagram, which will get very messy, I will draw the square base, PQRS, over here. So just like this. So all I've done is just taken PQRS and shown you sort of a bird's eye view. And that point that is right here, it represents straight down from X. Now I could call it X, but I'll call it Y just to avoid any confusion. So that's this point right here. So on my diagram, it will be somewhere around here. It doesn't really matter where you draw it, as long as you sort of understand the question. So where it is located is not really important. It's the mathematics that will determine the answer. So approximately there, let's say. So let's label this now. This is Y. And now we need to draw in some letters to help us with the algebra that's involved. Now, first of all, let's keep in mind what it is that they want us to figure out. They want us to figure out the maximum possible area of PQUT. PQUT is right here. So if this is the length, this is the height, so the area of that would be L times T. So they want you to figure out basically the maximum value of that. So maximize L times T. Now, L is that length, but the base is a square, so that is also going to be L. So this is L, and this is L, correct? And since this is the height, this distance from X down to Y is also the height. So I can just squeeze in the H right there. Okay. Now let's go back to this diagram here and start labeling this so that we can do some algebra. The first thing I'm going to do is draw some perpendiculars, these types of perpendiculars, from that point called Y to the other side. So there's one perpendicular, 90 degrees. Here's another perpendicular, 90 degrees. And let's start labeling this now. I don't want to introduce too many variables, only enough variables that are necessary. So first, we'll call these distances A, B, and C. All right. And then we're going to have to label a few more. But first, let's work with those three so we can take this one step at a time. So P to Y, I had labeled A. Q to Y, I have labeled B, and R to Y, I had labeled C. So let's carefully look at any Pythagorean relationships, and we've got a few of them. The first one, of course, is this one right here in this triangle, that h squared plus a squared is 12 squared, which is 144. The next one, of course, would be this one right here. That would be h squared plus b squared is equal to 10 squared, which is 100. And then the other one would be right here, which is h squared plus c squared is equal to 8 squared, which is 64. And my goal is to get similar Pythagorean relationships over here so I can solve this problem. Well, I have to unfortunately introduce a few more variables. Not the best thing to do or favorite thing to do, but it's required. So from here to here, I'll call that E, and therefore this would be L minus E, that distance. And I think one more will be sufficient. I'll call this D, and therefore from here to here will be L minus D. And then therefore from here to here is also E, and from here to here is L minus D. All right. So now, what can we get from Pythagoras? This triangle gives us a relationship with B in it, so I'll put it in this section. E squared plus L minus D squared is equal to B squared. And then for A, to put in this column of the diagram, we can use the triangle here. That would give me E squared plus D squared is equal to A squared. And then to put here, I'm going to use something with C, obviously, and that's this guy right here. So that would be L minus D squared plus L minus E squared is equal to C squared. All right. So now let's see what we can get. We can make some substitutions at this point. So for example, for A squared, we can substitute this guy. So we can just put H squared instead of A squared, E squared plus D squared, and that's equal to 144. All right. And in a very similar way, instead of B squared, we can put all this. So it would be H squared plus E squared plus L minus D squared is equal to 100. And very similarly, instead of C squared, we can put this, and that would give me H squared plus L minus D squared plus L minus E squared is equal to C squared. Or sorry, 64. Okay, so now we've got those. We'll call this one equation 1. We'll call this equation 2. We'll call this equation 3. So now, let's work with these equations. The first manipulation or combination of these three is going to be 1 minus 2. So if I take equation 1 and subtract from it equation 2, I will get the following. The h squares and the e squareds cancel, and all I'm left with is d squared minus L minus D squared on the left side, and on the right side it will be 144 minus 100. And when you expand this out, you get d squared minus L squared plus 2LD minus D squared is equal to 44. And that will give me 2LD is equal to 44 plus L squared, and D is equal to 44 plus L squared over 2L. All right, pretty good so far. Now, my next piece of algebraic combination or manipulation will be the following equations. Equation 2 minus equation 3. So that one will give me, let's see, the h squares will cancel and the L minus D squared will cancel. So the only thing left will be E squared minus L minus E squared, and on the right side 100 minus 64. So expanding this, you get e squared minus L squared plus 2LE minus e squared is equal to 36. The e squareds cancel. We are left with 2LE is equal to 36 plus L squared. That means E is equal to 36 plus L squared over 2L. All right. Now at this point, we've got something for D, we've got something for E. And that's helpful because we have an equation that has E and D in it. And that equation is right here. Equation 1. So let's substitute the values for D and E into equation 1. So let's give ourselves plenty of space for that. So let's remind ourselves what was equation 1. It was h squared plus d squared plus e squared is equal to 144. H squared is just going to be like that. D we had just solved in terms of L. It was 44 plus L squared over 2L. And that's all squared. And as you can see, it was right here. 44 plus L squared over 2L. And E we had also solved in terms of L. It was 36 plus L squared over 2L. And of course we have to square all that, and that's all equal to 144. So that's what we're doing now. Now we have to expand all this. So here we go. We've got some algebra to do. Let's put those over onto the other side. And when I do, I'm going to square the bottoms only. And when I do, I get 4L squared. And then this one, I'm also putting it on the other side and then squaring the bottoms. And then multiply through by 4L squared. That will get rid of all the fractions. So then you'll have this 144 times 4L squared. And then the bottoms cancel out. So 44 plus L squared, all squared, minus 36 plus L squared, all squared. Right? And now we can expand all this out. And 4L squared, H squared will remain at this side. Now, let's keep in mind or remind ourselves what it is that we're trying to figure out, because sometimes the question becomes so long we forget. We are trying to maximize, if we remember, L times H. Well, we have something like LH. We have its square, actually. We have L squared, L squared, H squared. And that's fine. If we're trying to maximize LH, it's sort of like the same as trying to maximize L squared, H squared. Or trying to maximize L squared, H squared times 4. It's the same thing. So we'll just keep it. Instead of dividing through by 4 and taking a square root, we don't need to do that in order to make it look like this. This is perfectly fine. Okay, so we're going to try to maximize this. And at the very end, when we get the maximum value of that, then we can divide by 4 and take the square root. All right, so let's expand all this out. We've got a little bit of algebra to do here. So this is going to be 576L squared. And let's see here, minus 44 squared plus 88L squared plus L to the power 4 minus 36 squared plus 72L squared plus L to the power 4. And so this will be 576L squared minus 1936 minus 88L squared minus L to the power 4 minus 1296 minus 72L squared minus L to the power 4. Let's collect like terms. 2L squared. Collecting all the like terms for L squared gives me 416. And then I've got minus 3232. Okay, so I've got it in a pretty good form now. Let's see. At this point, How do I maximize this? Well, you have to do something called completing the square. And in a very basic way, what that means is that if we have a graph, and the graph is a parabola, and because this is a negative, it's going to point downwards. That means at some point, you're going to get a maximum. So if this is, say, the value of L, and this is f at L, that for some value of L, whatever it is, f at L will be at its maximum. Now, how do we figure out what is that value of L? Well, that's what completing the square does. So here we go, completing the square. What you do, first you have to factor it out, the coefficient out front. And when you do, you get L squared minus 208 L squared plus 1616. Now to complete the square, what you do is you take half of this and square it. So this becomes 208 L squared, remains that. But now what you do is you take half of this and square it. Half of that is 104, and then you square 104. So plus 104 squared. And then immediately you have to subtract it, because you can't just add something. And then, of course, don't forget that 1616. What this does is allows you to very nicely factor those three. And when you do, it becomes L squared minus 104 squared. And then you have to kick these guys out of the brackets, these guys. But when you do, you have to remember to multiply by that guy. Don't forget that. So it becomes plus 2 times 104 squared minus 2 times 1616. So this is minus 2 L squared minus 104 all squared. And this becomes 21632 minus 3232. And finally, that is going to be minus 2 L squared minus 104 squared plus 1840. And let's not forget what that was. It was 4L squared, 8 squared. Okay, so now we are pretty much done with the question. This means that when L squared is equal to 104, right there, that part becomes 0, and it makes this have the maximum value. Max value is 18400. For what? For that function, which is equal to 4L squared, 8 squared. Okay? So, let's figure out now what is the value of just LH, because remember we had to maximize LH. All right, so we got that 4L squared 8 squared has a maximum value of 18400, and that happens when L squared is equal to 104. Well, divide both sides by 4, and you will get 4,600. And then take the square root of both sides just to get LH. And when you do, you get 67.823. And there you go. That is the maximum value for L times H. 67.823, and that would make number 25. The closest value is B.